This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
All right, welcome to another episode of Design Safe Radio. I'm super excited today to talk to Brady Cox from Utah State University, and man, it's been a while since we've chatted. I was just saying before we got on here, I think the last time we talked, you were still the PI at University of Texas Shaker Fleet, and it's really good to see you're still working with them, and good to see you again, man.
Yeah, it's good to be here. I appreciate you inviting me on to the podcast here, and happy to talk about NERI at UTexas, our large mobile shaker facility.
So we're seeing these massive machines behind you on the Zoom background here. Can you give us a little bit about these just amazing trucks that are in the fleet?
Yeah, you bet. So we have a number of trucks at our site. Our three main trucks are shown in my Zoom background, and I'll point them out. So this truck here, this one's TRex. TRex is, as far as we know, the only triaxial vibrosized shaker truck operating in the world. And what that means is that TRex, at the push of a button, can change from shaking vertically to horizontally crossline and horizontally inline. So it's a really unique piece of equipment. TRex is about 32 feet long and about 8 feet wide, so it's not much wider than a normal vehicle, but it weighs over 60,000 pounds.
Oh my gosh.
So the equivalent of that would be, let's say, about 10 Suburbans. Okay, so if you had 10 large Chevy Suburbans piled on top of one another, that would be the weight of TRex. TRex, let's see, can shake at a wide range of frequencies. So many cycles per second, we call that hertz. Okay, so 5 cycles per second, TRex can shake at, which is relatively slow. But you think about 5 times per second, that's kind of fast to us. But it can go up to over 100 cycles or times per second.
Wow.
So it kind of has a broad range of frequencies that it can generate these dynamic forces. Essentially, we're in a really rough description, we're simulating earthquake waves. Liquidator, this one over here, it looks very similar to TRex, but it's different. It weighs a little bit more. It actually weighs over 70,000 pounds, so it's a little bit heavier than TRex. But Liquidator right now, it really only shakes vertically, but it was designed to shake to quite low frequencies, so as slow as a half of a cycle per second.
Whoa.
Which allows us to generate longer waves, we call them, so we can look deeper into the ground.
And Liquidator, if I remember right, seeing a demo of it once, it'll actually lift itself up off of that that big plate, orange plate in the middle, and it bounce up and down like a pogo stick almost.
It can indeed lift itself off the ground. So Professor Ken Stokey at the University of Texas, he modified Liquidator even beyond its unique capabilities, where it will lift itself off the ground and use its entire weight essentially to generate forces. And
Ken, if you're listening to this, you still owe me an interview at some point.
Okay, I'm sure he'll, if we can track him down.
We've been trying to wrangle him for years, but I know he is a busy guy.
For sure, yeah. But Liquidator is also unique in the world. It was custom built to shake at low frequencies, and there's no other truck in the world like Liquidator. This little truck right here, and if I spin just a little bit, you can kind of see it better. That one is called Thumper. And Thumper is a much more common type of shaker, a vibrosized truck. And so there's quite a few of those in operation, and it's used to shake at higher frequencies. So it has much lower force output, but it still is very useful to us. We call that our urban shaker. So when we, pull up with Liquidator or TRex, people's eyes get really big, and they're like, oh man, for sure they're going to destroy my house or damage my building or my bridge. But if we pull up with Thumper, people are a lot more calm and less likely to get excited. But it operates to higher frequencies up to about 500 times per second. It can so.
And that's like I've got a little bit of musical background, and that's starting to get into audible frequencies that are in the kind of low musical range.
Yeah, you can definitely hear it with your ears when you sweep through frequencies with Thumper. You can hear the frequencies changing, essentially the note changing that it's vibrating at. Yeah. And over here, kind of on the, let's see which way, this way, this is our big rig. So we have our own tractor trailer, our tractor and a trailer that we pull our vehicles around with, because TRex and Liquidator are too large and too slow to drive on the road. So we have to haul them around the country. And we indeed have taken them all over the US and also internationally. So TRex went to New Zealand a few years ago after the Christchurch earthquakes, and we left TRex in New Zealand for almost a year.
Wow.
Working on several different NSF-funded research projects.
That's a fantastic segue to my next question about, like, what types of problems do civil, geotechnical, other types of engineers solve with these trucks? Like, what are those grand research questions that they're built to answer?
Yeah, so we have a science plan where we kind of have three major categories of research that we use these trucks, to solve problems of engineering interest to society. And I actually, probably the best way to show this is to share my screen, if that's okay.
Yeah, go for it.
Because I have a couple of videos I think that will help, or animations that will help describe what's going on. So I'm going to hit share my screen, and hopefully this works. There we go.
Awesome, got it.
Great. So the three areas that we use these trucks for most often, they're not the only things we use them for, but the three main areas that have to do with subsurface imaging. So trying to develop 1D, 2D, 3D images of the subsurface. And I'm going to activate this video here. This application illustrated in the video animation is imaging of a levee. So, for example, we have thousands of miles of levees in our country where we really don't know how they were built historically. We don't have good records. And on occasion, when it floods, or possibly in an earthquake, if there is soil liquefaction, sections of these levees could fail. And when that happens, there's a lot of flooding and really dire consequences associated with that. But because we have so many miles of levees, we can't rely on traditional site characterization methods to scan and look for these weak zones. So, for example, we're working on ways to profile or image these levees by maybe towing sensors along behind the truck, shaking the ground, and trying to develop these scans or these images of the subsurface. And we're moving towards 3D site characterization, what we call full waveform inversion. That's a big topic in the future. So we use the trucks as a source for waves to probe or image the subsurface.
So you've got places like in this video, you had an example from New Orleans. I remember a few years ago, we did a workshop in St. Louis at a levee nearby. And these are, I mean, if anybody's been to New Orleans or knows anybody who's been down there, that's a big deal when those levees fail. I mean, that's what happened during Hurricane Katrina and caused billions of dollars of damage. And what it sounds like your team is doing, the Shaker Truck team is doing, is being able to say, hey, let's keep that from happening again. Let's look at what we've got. Let's no judgment on whoever built these. I'm sure they did the best they could.
Yep.
But here's where we're at now. And if a hazard event happens, it doesn't become a disaster unless there's something built there to affect, right?
Right.
And so we're looking to take an honest assessment of what's there and be able to make an improvement if we can, so that a hazard event doesn't become a disaster. If
exactly.
I'm hearing you right.
That's exactly right.
Cool.
The second area that we focus on is we call this nonlinear in situ testing, kind of some technical words, but we push sensors into the ground. So in this previous application, we're only keeping our sensors on the ground surface. In this type of testing, we're actually using a hydraulic ram on the back of the truck to push sensors in. So we push pore water pressure transducers, we push accelerometers or geophones into the ground, and then we shake the soil and we try and monitor the response of the soil. And we would do that to study soil liquefaction. So for example, we could go to a site and we could test the ground and try and determine how susceptible that ground is to liquefaction during an earthquake. And we've used this technique up in Portland not too long ago, where we were testing silty soils, which are really hard to characterize in the lab, but also bio-improved soils, where the researchers have used either precipitation from biological organisms that would cement the soil together, or even desaturate it and cause air voids in the soil, which would help prevent it from liquefying. So this is one application where we've looked at nonlinear testing ranging from small strains up to large strains to characterize, for example, soil liquefaction.
Awesome. Yeah, well, if you're a longtime listener of the show, we had one of the researchers from, I think it was Portland State University up in Oregon, talking about those biomediation methods and that test that you guys did up there. It was fascinating to hear about, just what you're able to do with, at least on the order of magnitude, fairly affordably mitigate liquefaction, like compared to traditional methods where you might be putting big posts or pillars in the ground or relocating buildings or what have you.
Yeah, and that's one of the interesting aspects of our site. We're somewhat unique in that we're not confined to a lab. We believe that there's obviously a lot of great research and things that can be done in labs with scaled down models and testing. But ultimately, at the end of the day, we need to implement these methods on real projects, real sites, full scale. And that's one of the cool things that we have the opportunity to do by taking our shaker trucks to excite structures and real soil deposits in situ. That kind of
you may
brings
be able to, and I think you guys have done this on a number of occasions, of a researcher wants to study a particular site and make some improvement to it. They'll have a soil characterization cycle done. They'll make a scale model of a structure and the soil profile and put that at the geotechnical centrifuge at our friends at UC Davis. Make sure that it matches the full scale, do some sort of improvement or build something, and then they'll be able to bring that full scale, having validated it in the lab. Is that kind of how things go with you guys?
Absolutely. Yeah, it's good to work on putting all the pieces of the puzzle together, from in situ to smaller or lab scale versions, or using the centrifuge to scale up models, because each piece is important to putting the whole puzzle together to see the big picture and making sure that your designs are as good as possible.
Yeah. And so in your video here, you've got a little bit of a scale on there, but for those who don't have the advantage of YouTube, how far down are you putting these sensors?
So depending on the testing configuration, it might be within several meters of the subsurface. So let's say the top 10 feet, but it could be deeper. It could go down to 8 to 10 meters, so approaching 30 feet perhaps. And that's about as deep as we've done this so far. And that's just because we're limited on how large of strains we can develop in the ground. And what's shown here is we have what's called a drilled shaft or a drilled pier. This is a concrete pile that's been installed in the ground. And then if we shake on top of it, we can carry these large strain waves deeper into the soil.
Wow.
Otherwise, if we step back a little bit, we might be shaking just right on the ground surface and testing soils that were closer to the surface.
Oh, okay. Cool.
Yep. So the last of the three major areas we're studying is structural health monitoring and soil structure interaction, where we would use our shaker trucks and associated instrumentation, different sensors, and put them, for example, on a bridge. And then we could move the truck around on the bridge and shake in different locations and have a really controllable source in terms of its amplitude, but also its frequency range. And we can shake not just on the structure, but we could, for example, pull around and shake on the ground away from the bridge or the building, and we could send waves through the soil into the structure.
Oh, wow.
Which allows us to study what we call soil structure interaction. Again, in a rough sense, simulating waves that would be traveling from an earthquake through the ground, impacting the foundations of the structure, getting carried into the structure through the foundations, and then exciting, in this case, a bridge.
Now, this is a really hot topic in civil engineering, just especially in the United States. Our bridge infrastructure is woefully inadequate in a lot of places. And, you know, you've heard, if you've been in this world for any length of time, just study after study of the decay of our bridge infrastructure. And it sounds like, you know, what you guys are doing are one way to be able to truly characterize the level of decay of a particular bridge, and is it still adequate to carry the loads it was designed for, and things like that.
Yeah, you bet. You bet. A lot of our bridge inspections right now are, we rely on visual inspections, and in many cases, you could miss things that might be decaying or causing problems, whether that's under just static gravity loads or whether the dynamic loads of a large earthquake. So as we move forward in our future, we'll definitely be instrumenting more and more bridges, either with permanent or temporary instrumentation, and we'll be using dynamic methods to assess their abilities to carry loads and perform under extreme loading conditions like seismic events.
Wow. Yeah, it's amazing the variety of applications that you have for these very unique instruments. It's really cool.
Yeah, we enjoy it. It's pretty fun to be able to travel around the U.S. and around the world and take these trucks to work with researchers from many different universities and get to study and work on problems of interest to them and to our society.
Yeah, you mentioned the being able to deploy to Christchurch a few years back. Can you tell us about that? That was, I mean, just some of the videos that were coming out of that and the research coming out was just incredible. It sounds like a really interesting story.
It was. We went to New Zealand after the Canterbury earthquake sequence, or the Christchurch earthquake, to do two main projects. One regarding deep subsurface imaging, where we were trying to really look deep into the ground, because the soils in Christchurch are very, very deep, more than, let's say, a kilometer or 3,000 feet.
Wow.
Down to bedrock in many cases. And there's no economical way to drill borings that deep. We can drill that deep, but it's really expensive.
Yeah.
So we were going down there trying to help them develop profiles of the ground beneath all of their strong motion stations that recorded the earthquake.
Oh, wow.
So that we could build numerical models that would allow us to try and calibrate these models to be able to better predict the shaking that was recorded. Mm-hmm. We call that a backward analysis. So we wanted to do this backward analysis to make sure that we could predict the levels of shaking that were actually recorded in the earthquake, so that we felt comfortable then doing forward analyses or design in the future, where we're like, look, we now have a calibrated model and we know that it's accurate, and we can use that model now to better predict what levels of shaking will happen in future earthquakes, so that we can design our bridges, our buildings, our infrastructure, like our pipelines, to resist the shaking. So that was one project. The second project was related to the just pervasive soil liquefaction that happened. And in particular, we were studying a problem related to how to come up with economical solutions to mitigate soil liquefaction for residential structures.
Oh, wow.
In Christchurch, after the earthquakes, they had to basically abandon 10,000 residential properties.
Whoa.
And they basically tore down all of those homes and forced 10,000 families to leave. And we were trying to help a partnership between the U.S. National Science Foundation and the government of New Zealand, trying to come up with economical ways to mitigate liquefaction using various ground improvement techniques. So the contractors in New Zealand would install these different ground improvement methods, and then we would use TRex to shake those ground improvement measures and determine which ones were most effective. And then, of course, we would look at the economics of, which ones were both effective and economical.
Yeah.
So that was kind of the second major project that we used.
What did you guys find there?
So we found that there were a number of ground improvement methods that worked, and it depended on if you were trying to improve ground beneath an existing structure, like what would you do, versus if you have what we call a greenfield site, where it's a brand new piece of land and you're going to go and improve it before you build structures on it.
Okay.
So we found that some of the methods worked better than others. I probably won't get into the details here in this podcast. And also, some of them were more expensive than others.
Yeah.
And so we gave people kind of a range of choices that they could look into in terms of cost and effectiveness. And we did find some themes that were shown not to work very well. And what we did there was, just like we showed in one of those videos previously, we were pushing instruments into the ground and then shaking on top of the improved and the native soils to compare, how much the soil was improved against liquefaction.
That's awesome. We'll have to get with our team and see if we can link to some of those videos that you have there. You've got a TRex was actually creating liquefaction at some points, and you see water bubbling up, and it was really cool.
Yeah, it was a big project and a lot of interesting work for sure.
Yeah, awesome. So that's what's come before. Now you're on the cutting edge of some new stuff with this idea of fiber optic sensing system, this distributed acoustic sensing. I can't even pronounce it. DAS, the acronym's easier to pronounce. But using that to do subsurface and structural sensing. So can you kind of explain how that works and some of the advantages of that versus some of these more traditional methods with geophones and other sensors?
Yeah. So distributed acoustic sensing, or DAS, is a relatively new type of sensing. It's certainly new compared to other traditional ways that we've used in the past to measure vibrations. Historically, we record earthquake shaking with accelerometers. We call them strong motion stations. Broadband seismometers, which are good for recording more distant earthquakes. They're quite sensitive instruments. We would use geophones, as you mentioned. They sound like a phone, right? But it's a geophone, so it's listening to vibrations in the earth. So we put these sensors on structures, or we put them on the ground, and we try and measure earthquake waves or waves that we would generate maybe with our trucks. And we use those vibrations to tell us something about the response to this excitation, this dynamic loading. And in our case, one of the things we do a lot of is trying to image the subsurface. We've already talked about that. So the approach right now has been to basically have all of these individual sensors, and we have literally hundreds of them in our instrumentation pool for NERI at UTexas. And we go out and we put them on the ground in arrays or patterns. But even if we have like 100 or 200 sensors, which is quite a few, when we start to try and deploy them in arrays, we quickly run out of sensors. We can't put them over really large distances while still maintaining what we call good spatial resolution. So the really cool thing about DAS and using fiber optic sensing is that now our sensor is a fiber optic cable.
So the entire cable is a sensor.
The entire cable. And we can lay it on the ground, or we can bury it in a very shallow trench, or we can even hook up to existing telecommunications fiber optic networks.
Whoa.
That might be run by AT&T or Google or whatever. Okay, the same fiber optic cables that are used to carry your internet to your house, your TV. If
so you
anybody
could do something
still has
like
a landline in their home, okay.
So you could do something like there's I think this was a couple weeks ago where the island nation of Tonga was their fiber optics were completely cut off due to a submarine earthquake or volcanic eruption.
Exactly.
If you had, let's say this was 2 months ago, and you shipped one of your trucks over there, you could have hooked up to the subsea cable and measured the earthquake.
Yeah, so what we would do is we have something called an interrogator. And the interrogator, let's just call it a computer that we hook up to the fiber optic cable. And then that interrogator sends a laser pulse down the fiber optic. And if you've never seen a fiber optic cable or a fiber, it's almost the diameter of your hair. Okay, so they're really, really small fibers, and we send a pulse of light down the fiber, and it travels down the fiber, and it starts getting parts of the light, the laser, getting reflected back every time it sees a discontinuity in the cable. So every little imperfection in the cable is a signature in the pulse of light that goes down and back. And we can then excite the ground, hit on the ground, for example, and it will distort the cable just absolutely minimally. Like you would never ever be able to fill it with your body, your hands, your feet, or even sense it because the strains are so small. But the cable, the fiber optic cable, is slightly distorted, and it changes the pattern of the light that's reflected back and forth. And we can use about every meter along the fiber optic cable, we can have, it's like having a receiver. So we could bury a cable in the ground that's 1 kilometer long, 2 kilometers, 5 kilometers, 10 kilometers, up to 30 kilometers long. And literally we can record a vibration measurement every meter. So now you're talking about 30,000 receivers in a line, or we can bend it and create arrays. Mm-hmm. So it's the future of sensing. You can put the cable on structures, you can put it in the ground. Like I said, you can turn existing telecommunication networks into an array of sensors across parts of a city. And it's a really exciting thing. And it makes sense that we would then have this new fiber optic interrogator in conjunction with our shaker trucks, because we use the interrogator to record the vibrations and we use the trucks to generate the vibrations.
Yeah. So you could, let's say if you're building a new apartment building, you could embed fiber optic cable in the concrete and have a structural health monitoring system in your building.
Absolutely. Yeah, you could. And the good news is there's different types of fiber optic sensing that you can even have more spatial resolution than 1 meter. Like for acoustic sensing, right now the closest channel separation we have is about 1 meter. But if you go to distributed strain sensing and even distributed temperature sensing, you can shrink that down to the order of 10 centimeters or even less potentially. And so you can use different types of cables, fiber, I should say, installed in a single cable, and you can do temperature sensing, strain sensing, and acoustic sensing, all with one cable that you might install in a structure and then wrapping around in the ground, for example.
Wow. My mind is blown. It's just spinning of, wow, you could use it for this, this, like so many different applications, which is going to be good for future research, and any grad students listening out there going, ooh, that would be a really good thesis. Yes.
Yeah, we talk about smart infrastructure, right? Like that's what we want. And fiber optic sensing is going to help bring us into that next era in our field of study, where we're able to monitor our roads, our bridges, our buildings, our dams, our levees by just having fiber optic cable installed in and on and around these the things I've described, and then using it to measure how well the system is behaving as a function of time.
Wow, that's going to be fascinating to see how this evolves over the years. For those who are like, okay, this is cool, I want to follow along, see what they're up to. Where can people engage with the UTexas mobile shaker team and see what the research is coming out and follow along with where they're deploying and things like that?
Yeah, so we have a website on Design Safe, and if you just type in Google NERI at UTexas and mobile shakers, or Texas mobile shakers, our site will pop up. You'll be able to find it. And on that website, we have an overview of our equipment. We have resources, like we have a bunch of, every year we do 1 or 2 workshops related to the science plan, those 3 areas of study that we've talked about. And we have all the recordings from our past workshops. We just did one on distributed acoustic sensing in Louisiana back in October on a levee in conjunction with the U.S. Army Corps of Engineers and UC Berkeley. We've done a bridge testing workshop a few years ago in New Jersey with Rutgers University. We did a workshop regarding the biosol improvement with the folks at Portland State. And so, like, all of that information is on our website.
Yeah. Excellent. Well, we'll make sure to link to that in the show notes. And hey, Brady, thanks for joining today. It's been good chatting with you. And I mean, like all of our sites, it's like, oh man, we do a lot of cool stuff. So it's fun for me as much as anybody listening, just to be reminded how awesome of a team we have at the various NERI sites. And I just really appreciate you taking the time to chat with us about it today.
Yeah, you're welcome. And we are grateful for the support of the U.S. National Science Foundation to establish all of these really amazing sites. And I agree with you. Every time I visit one of our other NERI sites, it's just incredible, the work that's going on, and really, really cool stuff.
Yeah. Thanks for joining today, Brady. Well, hopefully we'll see you at EERI or something soon and get together. It'll be great. Take care.
All right. Thanks a lot, Dan.
Thanks for listening to today's episode of Design Safe Radio. This show is sponsored by the National Science Foundation grant number 1612144. You can subscribe to Design Safe Radio on iTunes, Stitcher, or wherever you find your podcasts. Please leave us a review so we can improve the show. Please also help others find our episodes in iTunes. Thanks for your feedback and support. You can find out more about NERI at designsafe-ci.org, on Facebook at Design Safe Radio, or on Twitter at NERI Design Safe.